All right, the artificial intelligence revolution is obviously here. It feels like it's changing everything. But behind all the magic of models like ChatGPT and Gemini, there's this enormous hidden crisis brewing. And believe it or not, it connects our entire power grid to, of all places, your kitchen.
You heard me right. It's not just that AI is using a ton more electricity, it's actually making the quality of the power flowing into your home worse.
I know. That sounds totally bizarre, but it's true. You know that rattling or humming sound you sometimes hear from your fridge or maybe your air conditioner? That's actually a sign of mechanical stress. Turns out AI data centers can create these little distortions in the electrical current, and those tiny imperfections make motors vibrate and shake, wearing them out faster and, yeah, making that really annoying noise.
Just look at the difference here. On the left, that's what we want. A perfect, clean, smooth 60 Hz sine wave. That's what our grid was designed for. But on the right, that's bad power. See how jagged and warped it is? Those are called harmonic distortions. Now, there's a safety limit for this, around 8%. If you go above that, the lifespan of pretty much all your electronics, your TV, your washing machine, you name it, it starts to go down. And get this, studies are showing that homes near these huge data centers are way more likely to be over that limit.
So today, we're going to unpack this whole massive challenge. First, we'll dig into AI's invisible power problem. Then, we'll see why our grid is basically on the brink of a crisis. After that, we'll look at Big Tech's playbook for how they're trying to solve it, explore the whole efficiency equation, and then we'll end on a really surprising question. Could all this chaos actually be an accidental green revolution?
Okay, first up, AI's invisible power problem. See, the issue isn't just about how much power AI is using, it's about the very nature of how it works and the unbelievable thirst for processing power that it has.
To really get this, we've got to talk about the chips. For years, the hero of computing was the CPU, the central processing unit. Think of it like a really efficient electric car. It does one thing, and it does it fast. But AI models, they need to do thousands of things all at the same time. That's a job for a GPU, a graphics processing unit. And if a CPU is an electric car, a GPU is a monster semi-truck. It can haul a massive load all at once, but man, does it guzzle gas. A single top-of-the-line NVIDIA H100 GPU can use as much power in a year as a typical American house. A single one.
And the scale of this is just hard to wrap your head around. The amount of computing power, or compute, needed to train these models is just exploding. For perspective, a petaflop is about 1,000 trillion calculations per second. GPT-1 needed about 18,000 of those. GPT-4, a ridiculous 21 times billion. This trend isn't just an upward curve, it's a rocket ship heading straight up, and it's taking our energy demand with it.
So, where is all that power coming from? Well, that brings us to our electrical grid, which, frankly, is on the brink. Our entire grid is built on one very simple and very fragile rule. Supply must always equal demand, no exceptions.
And here's the real problem. A city's power usage goes up and down kind of predictably, right? But AI training creates something new and dangerous called synchronous demand. This is when tens of thousands of those semi-truck GPUs all slam on the gas at the exact same microsecond, demanding maximum power instantly. Our grid, which is designed for gentle slopes, is suddenly facing a vertical cliff. It just wasn't built for that.
And this isn't just theory, this happened. On July 10, 2024, in Northern Virginia, which is basically data center capital of the world, a little piece of equipment called a lightning arrestor failed. A tiny glitch. But what happened next was a massive warning. The voltage dipped for just a few milliseconds, but the super-sensitive data centers all flipped over to their backup batteries. In that single instant, 1,500 megawatts of demand just vanished. That's the amount of power the entire country of Iceland uses. Poof, gone. The grid was suddenly overloaded with power it had nowhere to send, and the whole system came dangerously close to a complete meltdown.
And let's be crystal clear, this is exactly the kind of domino effect that causes catastrophic, region-wide blackouts. We're talking about the kind of stuff that hit the Northeast in 2003 or Texas in 2021. The stakes here are incredibly high.
So what's the plan? This brings us to Big Tech's energy playbook. The giants, we're talking Microsoft, Google, Amazon, they've all looked at this situation and realized they cannot wait for the public grid to figure this out. So they've kicked off this wild race to just bypass the grid completely and build their own power sources.
And they are trying everything. We're talking huge investments in small, modular nuclear reactors, basically mini nuclear power plants. Microsoft has a deal to buy power from a nuclear fusion startup as early as 2028. That's literally bottling the power of the sun. Then you've got hydrogen fuel cells, Google drilling into the earth for geothermal energy, and even OpenAI's Sam Altman is backing new solar tech that can work 24/7. It is a full-blown private energy arms race.
But it's not as simple as just picking a solution. Let's take hydrogen for a second. Turns out there's a whole rainbow of hydrogen. Gray hydrogen is the most common, but it's made from fossil fuels and it's dirty. Blue is a little better. It captures some of the carbon. What we really want is green hydrogen made with renewables, but it's super expensive and hard to make. So now you hear about turquoise hydrogen, which is kind of a mix. The point is, making these new energy sources actually clean is a huge challenge all on its own.
So, making more power is one piece of the puzzle. But what about just using less power to begin with? That's the other half of this, the efficiency equation, getting way more work done for every single watt of energy you use.
And a huge breakthrough here is coming from a totally different way of designing chips, led by a company called ARM. These chips were originally designed for cell phones, where saving every last drop of battery is everything. Well, they're taking that same power-saving mindset and applying it to data centers. The results are amazing. Chips like the AWS Graviton can offer up to 60% power savings. That's a total game changer.
And that's just one piece. The industry is also racing to invent new liquid cooling systems that pipe coolant directly to the chips to cut down on air conditioning. They're trying to reduce the insane amount of water they use. Training GPT-3 drank 700,000 liters of fresh water. And they're trying to move more AI tasks on device, so the work happens right on your phone, keeping it off the power-hungry cloud in the first place.
And all of this brings us to our final and maybe most surprising section. Could this be an accidental green revolution? I mean, with all this talk of crisis and power shortages, it's easy to be pessimistic. But what if there's a silver lining? What if AI's massive energy problem is actually the catalyst we've been waiting for to build a cleaner future?
Now, here's the paradox. The upgrades AI needs to survive are the exact same upgrades a renewable energy grid needs to thrive. Think about it. You need giant battery banks to handle AI's sudden power spikes? Well, those same batteries are perfect for storing solar and wind power for when the sun isn't shining. You need to build new power lines for data centers. Those lines can also carry clean energy from the middle of nowhere to our cities. And maybe most importantly, AI's desperate need for power creates a huge financial incentive to finally modernize our grid, something climate goals by themselves have struggled to do.
So that's the real tension here, isn't it? On one hand, we are facing an energy challenge so big, it's pushing our entire infrastructure to the breaking point. But on the other hand, that exact same crisis is forcing a level of innovation in clean energy and efficiency that we have never seen before. So the big question we're all left with is this. Is AI's energy crisis the powerful push we desperately needed? Or is it the one problem that we just can't solve in time?